Hello, everybody. Welcome back to the Feynman technique. Um, Today, we're going to try to evaluate this integral right here. I have an idea for how we're going to proceed. I'm not sure if it's going to work. I'm pretty sure I can at least get this to an infinite sum. I don't know if the infinite sum we get is going to be something recognizable like pi squared over something, or maybe even pi cubed over something. But let's just see where this goes. All right, you can see this is what we should get. Let's go ahead and take a look at what this thing looks like. All right, so that's what it looks like. Goes to zero pretty quick as x goes to infinity. Let's see. I guess we'll just put that graph all the way over there and then zoom in. There we go. All right. So, I don't like working with exponentials, so right away, I think I'm just going to let u equal e to the negative x. That implies that du is equal to negative e to the negative x dx. Of course, e to the x is just u, and then we'll divide both sides by 1 over negative u and bring that negative out to the front. All right, so now let's go ahead and plug in that substitution. E to the negative infinity is 0, and e to the negative 0 is e to the 0 is 1. All right, x. All right, well, this implies that natural log u is equal to natural log of e to the negative x. And of course, this negative x can come right outside. And natural log e is, of course, 1. So, x is negative natural log u. All right. So, right here, we have negative natural log u, sine of negative natural log u, and e to the negative x is u, and then we'll have a negative 1 over u du. All right, it doesn't like part of this. I think it's this natural log u. There we go. All right, now let's clean this up a little bit. This negative can come all the way outside to cancel that negative, and we'll cancel this negative by switching our bounds of integration. There, that looks a little better. All right, maybe I can clean this up a little bit by putting this afterwards. I like to try to use as little parentheses as possible and still have Desmos understand what's going on. All right. Oh boy. Okay, so what are we going to do now? Well, this is one of my favorite tricks. Sine of natural log x is just the imaginary part of x to the I. So we'll use that. So we're going to say that I is equal to this, and then we'll have the imaginary part of x to the I, and we'll change our dummy variable back to x. All right, and then this imaginary part can come right outside the integral. Okay. Gosh, now what? Let's see. Okay, you'll notice that this and this are just x to the something. And if we take the derivative of x to the something with respect to that something, we will recover a natural log x. So what I'm going to do is let some function of t be equal to the integral from 0 to 1 of x to the t times natural log of 1 minus x dx. And now we can see more of our function there. Um, okay. Um, well, this means f prime of t is equal to the derivative with respect to t of this that we can take directly by taking the partial with respect to t of the integrand. So all that's going to end up happening is we're just going to get a natural log x there. And just to make sure, I'll take the derivative directly in Desmos right there and make sure they match up, and they do. So we can say that I is the imaginary part of our f prime of, let's see, our t would need to be, let's see, this is an x to the negative 1, so we can say this is x to the I minus 1. So it's going to be the imaginary part of f evaluated at I minus 1. Okay. Well, we can't really figure this out without doing some sort of series representation for this, and by extension, this and this. So let's make another representation for f of t. All right. So since I don't use these that often lately on this channel, I'm going to show how we get the infinite series representation for natural log 1 minus x, starting with 1 over 1 minus x is equal to the sum as n goes from 0 to infinity of x to the n, and that's good for x between negative 1 and 1. And that's fine because our bounds of integration are okay. Well, actually, it doesn't converge at 1, but we can get around that by taking a limit. All right, so we know this. So that means that if we take the antiderivative with respect to x on both sides, we can just bring this integral inside here. All right, so taking the antiderivative of 1 over 1 minus x, we get negative natural log of 1 minus x being equal to this. Antiderivative of x to the n is just x to the n plus 1 over n plus 1. And then, let's see, we can add a 1 and then subtract a 1. So this is true. So we will say that natural log 1 minus x is equal to the negative of this plus c. And c is very easy to solve for. All we do is plug in, since we're saying this is true, it has to be true for all x. We'll pick x is equal to 0. We get 0 is equal to 0 plus c. That means that c is 0. All right, so now we have that. All right, so let's rewrite our f of t using that. All right, so bring this negative out here, and it looks like I have an extra dx here. Okay, this x to the t can come inside here as a plus t on our exponent. Okay, and then we can switch the summation and integration. Bring this 1 over n outside. And then this whole thing right here is going to be evaluate to x to the t plus n plus 1 over t plus n plus 1 from x is equal to 0 to 1. The 0 term will cancel out, and the 1 term will just make this a 1 over t plus n plus 1. So t plus n plus 1. All right, now let's just check this. Yeah, that lines up nicely with our other f of t right here. Yeah. Okay. For some reason, Desmos does not like graphing infinite sums. So I have to plug in 1, then 10, then 100, and so on. All right, so f of t is equal to this, but we want f prime of t, so we can plug in I minus 1 for t and then take its imaginary part. So we need to take f prime of t as it exists here. All right, so what are we going to get? Well, this 1 over n is not going to change. This can be viewed as a t plus n plus 1 to the negative 1. So when we take the derivative, we'll recover a negative sign, and it will become that to the negative 2. And we'll just put a squared here. So that's what f prime of t should be. And let's just make sure that it is. Yeah, that matches up nicely with our f prime of t. Okay, so we know this. We know I is the imaginary part of f prime at I minus 1. So let's plug that in and take its imaginary part. Imaginary part, and our t is just becoming I minus 1. All right, minus 1 and plus 1 cancel out. All right. So means I is equal to the imaginary part of this. Now what we're going to do, let's switch this, make this an n plus I, and then multiply upstairs and downstairs by n minus 1 squared. All right, that's going to give us n squared plus 1. Downstairs, all squared, and if we FOIL this out, we should get an n squared minus 2in minus 1, right? I squared is minus 1. Yeah, we get a minus and minus, yeah, minus 1. All right. But taking the imaginary part of this part is going to go away. This part is going to go away, and this I will go away. Let's see if that's right. Yeah, that's it. That matches our original integral quite nicely. Now, I don't know of, let's just make sure this actually goes. Let's see if we can get that exact. There we go. All right. So if you do 100,000 terms of this, we're going to get, as far as Desmos is concerned, the exact same thing. So let's put our infinity back, and I'm going to plug this into ChatGPT and see if there's any sort of special function. Oh, look, that n and that n cancels. And then let's just bring this negative 2 outside. Negative 2. And now let's ask ChatGPT and see if there's any sort of special function representation for this. All right. Does have a special representation. Let's see what it spits out. The series does not simplify neatly into elementary functions. However, it can be expressed using special functions. In particular, oh, okay. So I should have taken a look at my Fourier series, and I might have been able to actually see that it was equal to this. Okay, but it looks like this is as far as I got. So I'm gonna leave it like that. So we can say this. Okay, and this is good enough. I mean, if you take, let's see how many terms it takes us to get to within 1/10,000. All right, 10. All right. Oh gosh, we're almost there. 14, 15, 16, 17, 18, 19, 20. Yeah, I mean, yeah. That's so if we took 20 terms of this, which is totally doable by hand, you have an answer that is within 1/10,000th of the actual answer, and that's usually good enough for like engineering and stuff like that. So I'm going to leave it like that. All right, guys, I hope you enjoyed that, and we will see you next time.